Last time we have introduced the formula about fringe resolved intensity autocorrelation trace. The formula is here. There are 4 terms. The first one is a constant. Second one is about G2 function, which is the normalized intensity autocorrelation function, or IA function, defined here. Okay, you can see it's time average of intensity times time shifted intensity. So it's an overlap integral. Okay, normalized to the average of I squared. So you can imagine when tau equals 0, the numerator is the same as denominator. You got 1. Okay, that's the maxima of G2 function. The third term is about a complex F function with carrier frequency omega 0. The last term is a complex G function with carrier frequency 2 omega 0. Do you know why there is a 2 omega 0? While in the previous section, field autocorrelation, we have only omega 0 tau term. We don't have 2 omega 0 tau term. So what's the major difference between intensity autocorrelation here and the field autocorrelation earlier?
The linear optics.
Yes, the only difference is you have second harmonic generation here. And that's why there is 2 omega 0 here. So basically, the fringe density of intensity autocorrelation trace could be even higher than the field autocorrelation trace because of the last term, 2 omega 0. Okay, here I show you one example. The blue curve is the assumed intensity profile. It has double peaks. Okay, you can main peak and a small side peak to the right-hand side. The red dashed curve is the phase in the time domain, and clearly it is a nonlinear curve, so it's a chirped pulse. It's not transform limited pulse. Okay. The corresponding fringe resolved intensity autocorrelation trace is shown in the second figure. Okay, so you can have a background normalized to 1 and the dense fringes underneath a certain envelope function. Okay, and if you pick up the envelope, you got the gray dashed curve here, which is the G2 function. According to the last slide, G2 function appears in the second term, right? Without carrier frequency, omega 0 or 2 omega 0. So this is the envelope, okay? And where is the constant term? Here, right? Even delay is very large. The constant term gives you some background, okay? And if you compare the width of G2 function and the width of the signal pulse, you can see they are different. In this specific example, the correlation width delta tau is 1.86 times delta t. Delta t is the FWHM of the signal pulse. So they are different. You can also notice that the peak value of the autocorrelation trace is 8 times bigger than your background. So the 1 to 8 ratio is an important factor that you can remember. Experimentally, when your autocorrelation trace does not have the 8 to 1 ratio, you know something is not ideal. Okay. Here I show you the complex F function appearing in the third term of the formula. The solid green curve is the envelope of F function. The purple dashed curve is the face of the f function. Okay, so it's a complex function. Information is contained within the fringe density variation, which is not very obvious, but you can perform data analysis to extract the f function, complex f function, from the data trace. In the fourth term, we have a complex g function, which plotted here. The green dashed one is the magnitude function of the complex g. The solid purple curve is the phase function of the complex g function. Okay, so they look different. Okay, f function and the g function are essentially different. But here we are more interested in the gray dashed curve here, the intensity autocorrelation function, the G2 function. And some characteristics can be shown here. G2 of minus tau, you can prove it's equal to G2 of tau. So that means your G2 function is always an even function. Okay? And if you check f function and the g function, they are like this. F of minus tau equals f of tau star. G of minus tau equals g of tau star. Okay, so that means the magnitude of f function is even function, but the phase of f function is an odd function, which you can witness in the third figure here, right? The green function is an even function, but the purple function is an odd function. Mathematically, you can prove f of minus tau equals f of tau star. Same thing in the g function. The magnitude is even, the phase is odd. Okay. Okay. This slide shows something interesting. I try to compare the autocorrelation traces due to transform limited pulse and the chirped pulses, but they share the same intensity profile, I of t. Okay, so if the input pulse is a transform limited pulse, okay, you have maybe a Gaussian shape, the blue curve, and your phase is a constant phase, phi of t equals 0. So this is the signature of transform limited pulse. And the computer simulation tells you the corresponding intensity autocorrelation trace look like this. And we also know the envelope of the trace corresponds to the intensity autocorrelation function, G2 function. Okay. Now, okay, in this case, the correlation width is 1.41 times delta t. The correlation width is 1.41 times bigger of the intensity FWHM of your input pulse. This number is fixed for Gaussian pulse. Okay, here I assume a Gaussian profile for this simulation. If it is Gaussian, then the ratio is fixed. Delta tau over delta t is 1.41. Actually, square root of 2. Okay. Then I change the temporal phase. Okay, you see I have a parabolic temporal phase, but I maintain the intensity profile, I of t. So the second intensity profile is the same as the first intensity profile, the same shape, the same width. They only differ by the temporal phase. Then what happens? Okay, according to the theory, the G2 function is dependent on your intensity profile, I of t only, right? So if you have the same I of t, you too should share the same G2 function. So as the first case, okay? But the fringes could be different, okay? So in the simulation, I got a fringe like this. You have a different fringe resolved intensity autocorrelation trace. Although they have the same G2 function, they have the same envelope function, but they have different fringe resolved autocorrelation traces. I'm sorry. Can you tell the major difference between these two cases? What is the major difference? 有相同的包络，但是细节不一样啊，我们一看就知道不一样。但是你可以清楚的说出来是哪里不一样的。Yes.
The carrier inside its magnitude is not a constant to the it's not constant times the envelope, so it's 更容易用英文说，
中文也行。
就是它再也不是一直都，就是它离开中间的时候，它那个正的幅度会变小。
Good, good. You have identified the major difference. In the first case, you see the top of fringes always in contact with the envelope, right? But not the case in the second example. You see envelope is still here, but the fringes top are not in contact with the envelope. Okay, so there are blank regions here and here, right? This is the signature of chirp pulse. Okay, so that means although the intensity profile I of t and I of t minus tau, the two intensity profiles, are still partially overlapped. As long as this happens, the envelope is here. The envelope will not drop to 0 as long as there is partial overlap, right? But as we mentioned last time, how about the fringes under the envelope? If I of t and I of t minus tau overlap with different fringe densities, which would happen in the case of chirp pulse, then the interference would be different. Okay? Then that's why there is destructive interference here. You cannot get high interference power, so you see the signal drops. Even though the intensity still overlap, you got G2 function. G2 function value is not small, but your interference is kind of destructive. Okay. So whenever you perform your experiment, you got raw data trace, and after data processing, as we will introduce, you got G2 function. You plot them together against with each other. If you see some blank regions, you know your pulse is chirped. Okay, that's a simple way to distinguish whether your signal pulse is chirped or not. Okay. If you only look at the envelope G2 function, you have no idea whether your pulse is chirped or transform limited. But if you can compare the envelope with the fringes, you got more information. Okay. The next question is how to retrieve the G2 function from the raw data trace. It turns out that the process is very similar to the process we used in field autocorrelation retrieval. Okay? Based on Fourier transform. Step 1, we perform Fourier transform for the data trace. Okay? So the blue one is the raw data trace shown here. The red one is the Fourier transform in red color shown here. How many components have you observed? 5, right? Centered around 0, plus minus omega 0, and the plus minus 2 omega 0, which is natural according to the formula. Okay? In step 2, we extract the component centered at 0 frequency, kappa equals 0, which is shown here. I use a rectangle here to highlight what we need. But be careful, due to the constant term in the formula, after Fourier transform, you got the delta function, right? So it means you have a very narrow and sharp peak at kappa equals 0. But the information is not what we want. It is just a constant. We need G2, right? So you need to delete the delta component while preserve everything else at the DC band, okay, or the baseband. And this is the Fourier transform of G2 function, or G2 tilt of kappa function, okay, in step 2. And if you review what we did in the analysis of field autocorrelation, which component did we retrieve? At that time, it's not the DC component, right? It's the first harmonic component centered at omega 0 at that time. But this time, we need a DC component. And very trivial, you just perform the inverse Fourier transform, you can recover the G2 function, which is the green curve shown in the third figure. Okay, just 3 steps. Fourier transform and the filtering, inverse Fourier transform. You got what you need. Okay. Any question? Maybe you can think about in what occasion this process will fail. Is this process always functional, or sometimes it will no longer work? The hint is, look at the central figure, okay? If you have 5 well-separated components, this scheme will work. But if they are overlapped, can you still get G2 function in this way? No, right? And in what occasion these 5 components will overlap with each other? In what occasion? Good, you have seen why they are separated. It's only because the carrier frequency omega 0 is much larger than the bandwidth, right? If the carrier frequency is around the bandwidth, then these 5 components should overlap with each other to some extent. Then low-pass filtering in step 2 will no longer work, right? After low-pass filtering, you will not only get G2, okay, but also the information about F function, and even the information about G function. Okay, it's not clear. They are overlap with each other. Okay, so in the case when your carrier frequency is similar to your bandwidth, this scheme will not work. And what does this mean? Your carrier frequency is close to your bandwidth. What does this mean? It means octave spanning spectrum. Or in time domain, it means single cycle pulse. Okay? Your pulse envelope, the width of your envelope is similar to your carrier cycle. It's called single cycle pulse. In that case, this scheme will not work. Okay. But as you might have known, people can produce single cycle pulse now. So there must be some solution, right? This will not work. You need some other method. Okay, we can talk about this issue later, but here is just reminding. Okay, and then if you compare with the original signal pulse, intensity profile is shown here, the gray shaded area. You can see the G2 and the I of t look different. Okay, so even you get the G2 function, it does not tell you what does the pulse shape look like. Okay, they are basically different.